Yesterday you guys were introduced to waves, and I wanted to run through this with you real quick, make sure everything is making sense, make sure everything was doable. So real quick here, A is pointing to the top of the wave, so that's a crest. B is pointing from one crest to the next crest, so that's a wavelength. And remember, the symbol for a wavelength is the Greek letter lambda, that upside down Y looking thing. C is from the rest position up to a crest, so that's an amplitude. D is the lower part of the wave, the minimum amplitude if you will, so that's a trough. E is also an amplitude. It's from rest to trough. So remember, an amplitude can go either way, it can go above or below. F is from this point on a wave to an identical point on the next wave, so that's also a wavelength. And then G is what we call the equilibrium position, right? If the wave stops, that's where everything will come back to. That's the equilibrium or rest. Alright, the wave trains below all have the same speed, so imagine they all started here and they're moving to the right. Okay, it says write the number of waves shown on each one. I always have to cheat and put in this equilibrium line, okay, and then I can count. But other than that, it's too hard for me. So there's my equilibrium line. So here's half a wave, one and a half, 1.5 waves. Okay, this is one full wave. This is 1, 2, and then the top half, and then this is just the top half of a wave. Okay, write the number of waves shown. Did that. Which wave has the longest wavelength? Long wavelength. Well, this one doesn't even fit on the page. So D. High frequency. C's got the most crests going by, so C. Shortest wavelength, that's also C, and the lowest frequency, well, D is the least frequent wave there. Okay. Alright, and then there were some wave equation problems, and we have the equation that tells us the speed of a wave is given by its wavelength times its frequency, or its wavelength divided by its period. Those are identical equations. Now, you notice while fishing that wave crests pass by your anchored boat every 3 seconds. Okay, that tells you here's the front of your boat. Every 3 seconds, a crest comes by. That actually just told you the period, if you think about it. It tells you for one complete wave to go by, that's 3 seconds. Furthermore, it says whenever there's a crest at the front of the boat, there's also a crest at the back of the boat. So we have a wave here, there's another crest over here. Okay? And the boat is 4.5 meters long. Okay? How fast are the waves traveling? Okay? So we can use this equation. A wave travels 4.5 meters every 3 seconds, okay? And that's 1.5 meters per second. Okay? So that one was pretty straightforward. Number 4, sound wave with a frequency of 262 hertz travels through the air at 343 meters per second. So we're given a velocity of 343, we're given a frequency of 262, and we are asked to find the wavelength. Okay? And this is in meters per second and hertz, so we don't have any unit conversions to deal with. Just V equals wavelength times frequency. So put in what we know and solve for what we don't. 343 equals 262. And we can find lambda. Okay? So 343 divided by 262 equals 1.3 meters. Okay? We don't think of a sound wave as having a length, but it does. The musical note D has a frequency of 587.33 hertz, so F equals 587.33 hertz. And a wavelength, lambda, of 0.579 meters. Find the speed of sound. Well, V equals wavelength times frequency. So if I take 587.33 times 0.579, it's 340 meters per second. Okay? Now, you'll notice in the problem above, I had it as 343. Down here, it's 340. Both of those are legitimate numbers for the speed of sound. 6. AM radio waves have frequencies between 550, that's kHz, that's kilohertz, and 1600 MHz, that's megahertz. They travel at 300 million meters per second. That's the speed of light. What is the range of their wavelengths? So if we look at AM waves, we know a frequency of 550 kilohertz, or 550 times 10 to the third hertz. Okay, their upper frequency is equal to what does it say there? 1600 megahertz. 1600 times 10 to the sixth. I don't know what that was. Times 10 to the sixth hertz. Okay, so if I want to know their range of wavelengths, V equals wavelength times frequency, so I can say wavelength is equal to the velocity divided by the frequency. So I'm going to take 3 times 10 to the 8th divided by 550 times 10 to the third. Okay. So 3e to the 8th divided by 550 e to the third, okay, and that gives me a wavelength of 545 meters. Of course, this becomes for the lower range, right? So this is the longest of the wavelengths. If I go up to 1600, then 3 times 10 to the 8th divided by 1600. You got to be careful. This one's times 10 to the 6th is 0.1875. Okay, so these wavelengths range in length from 20 centimeters long, basically a foot, all the way up to 545 meters, or about a third of a mile long. Okay, so the AM radio waves, kind of a big deal. FM waves have the same speed, but range in frequency from 88 megahertz to 108 megahertz. Okay, I almost wonder if I have a typo there, and that should be KHZ, but oh well. Okay, 88 megahertz to 108 megahertz. It's exactly the same process. V divided by F equals lambda. Okay, so hopefully that was okay. Now this leads us to one question though. If V equals wavelength times frequency, what determines the speed? Okay, how do you make a wave go faster? And this is sort of an interesting question because it only depends on the medium. Okay? And so I want you guys, I think what we're going to do is try to investigate this a little bit. And I have big springs that you can stretch out and you can play with. And basically what I want you to do is I want you to test a couple different things. How can you get a wave pulse, right? Just a single pulse to get from one end of the wave to the other faster. Okay, I'll get a document put together for you where you can try to test some stuff, but I want to see, how do you get a wave to travel faster? How do you change the speed of a wave, faster or slower? Alright, hopefully all that makes sense. Let me know if it didn't, and we'll do a lab today.